Hi everyone, welcome to my YouTube channel and let's talk about these problems. So as you can see, we have 6 problems to cover in this video, and while if you look at my past videos, I mostly talk about one problem for one video, but I think in this case we have 6 problems, and don't get scared, like all these problems you can solve this making like tiny bit of change in our code. So let's let's work on this problem. So here we have 6 problems. They are very similar. As you can see here, like for Leetcode 1-to-1, we have one transaction allowed. The next one, unlimited transaction. For the next one, at most 2 transaction. The next one, we have K transaction, and so on and on and on. So you can see that they are very similar, right? So we have 6 problems to cover, and let me start with 188. So I know it is labeled hard, but I think this is very doable. But unfortunately, when you look at the Leetcode solution, almost all of them are, solved by using greedy approach. And my issue with greedy is that you have to show that greedy approach works. And unfortunately, in many of the Leetcode solutions, like some people can come up with greedy approach, but then they don't show why greedy approach works. So they don't show why greedy approach works. And you have to show that those greedy approach works by proving them, right? Using the induction. But anyway, these problems is can be solved by using dynamic programming. So let's see how we can solve this. This is the first problem we will solve together. So I want you guys to pause this video for a second and try to come up with your own dynamic programming solution. Okay, so let's look at my solution for this problem. So as I mentioned before, if you look at the solutions posted on Leetcode, many of them use greedy approach, and my issue with them is that they rarely show why greedy approach works. And to show why greedy approach works, you have to use induction, but that's for another topic. But so let's use dynamic programming for this problem. If you look at DP, well, we have to enumerate all possible cases, and we have to use exhaust all those possible cases, right? That has been about Fibonacci. We had to have a optimal substructure and overlapping subproblems. So if you look at this problem, how many states do we have to consider? We have a trend. We have to consider about the recurrence relationship for our states, and how many states do we have to consider for this problem? We have, we are given this price array, and we are given K transaction. And there's one more thing, right? On a given day, you can either buy or sell a stock, right? So we have 3 states to consider. So that's the number of transaction and where we are in our price. So meaning, in other words, we are on say, I don't know, like ETH day, or I+1 day, something like that. And then the last case, this is important, I think. So whether we have a stock in our position or not, this part is the key. So we have 3 states to consider. That means we have 3-dimensional DP table, right? So this third state is a little bit tricky, and in my solution I use 2 states for this guy. So whether I have a stock, that's 1 state, or whether I don't have a stock. So I have two states to consider. And let's say S is a set with 0 and 1. So that's for this case 3. And when S is equal to 0, that means right now we don't have a stock. When S is equal to 1, that means we have a stock. Okay. So you may wonder, how does that translate to, say, we buy a stock or we sell a stock? Well, that's a good question. Before we get to that, so we have our DP entries will be something like this. We have DP of I, j, s, where I is from 0 to n-1, where n is the length of price. J is our number of transaction we have right now. So J will run from 0, 1 all the way to K. And S is our whether we have a stock or not. So we have two states. Like for instance, you can put, so this order doesn't matter as long as you are consistent. Yeah, let's see. So our code for this kind of problem will look something like this. So we iterate from I equal to 0 all the way to n minus 1. That's this guy. And then for j, from we are actually starting from k all the way to 1. Here, notice that I put 0, not negative 1, because as we will see later, when j is equal to 0, that's actually part of our initial condition. So when you set this equal to negative 1, then it will change, it will modify our initial condition and we will get a wrong answer. So that's something that you have to keep in mind. And then for s is equal to either 0 or 1, then we have a dp, right? And then we return our the answer. So in that case it will be something like dp of negative 1, the last entry, and then we would have, say, k, and then we would have 0. Okay, so forget about this for now. And so recall that s equals 0 means we don't have a stock. S equals 1 means we have a stock. So that's something that you have to keep in mind. If you have taken, say, Markov process in probability class, we have a transition matrix. So I think that may be helpful, like understanding what's going on here. So here I have a transition matrix for our s. So we have, say, here these are all s, and this guy will be what? S of 0, 0. So that's in other words, you can say that this corresponds to, say, we are moving from s equals 0 to s equals 0. What does that mean? Like, this is all just a bunch of mathematical notation, but when we are moving from s equals 0, meaning that we don't have a stock, to we don't have a stock, we actually didn't do anything, right? We didn't buy a stock, so we don't do anything. In that case, that corresponds to this guy. We do nothing. Same thing for s equal 1. Same thing for moving from s equals 1 to s equals 1. That means in previous state we had a stock, and currently we also had a stock. That means we didn't sell a stock, right? So we didn't do anything here. For this guy, so that would be s of 0, 1. So if we are moving from s equals 0 to s equals 1, what does that mean? Initially, we didn't have a stock, but in the end, we had a stock. That means we purchased a stock. So we bought a stock. And for s from 1 to 0, 1, 0, that means we had a stock initially, but then in the end, we didn't have a stock. So that means we sold a stock. We sell a stock. I think understanding this transition matrix is the key for this kind of problem. So in dynamic programming, the most difficult part is actually how do you define dp? What is your definition of dp matrix, this dp? If you can come up with really great definition of dp, and then you find this transition matrix, finding the recurrence relationship is a little bit easier. A lot of thinking goes into how to formulate the problem. I think that's the hardest part for dp. Here is my transition relationship or recurrence relationship. dp of I, j, 0. That means the maximum profit we make with j transaction remaining on the ith day, and we are not holding a stock. And that is just, we take the maximum of dp of I minus 1, j, 0, or dp of I minus 1, j, 1 plus price on ith day. Now, let's forget about this mathematical notation. What does this mean, in plain English? Notice that we are so here notice that we have I minus 1. Here we have I, so we are actually moving from here to here. So initially we have j transaction remaining here, and s equals 0 means we don't have a stock. We don't hold a stock. On ith day, we don't hold a stock. So that means this guy, we didn't do anything. So we didn't do anything, and the next guy is what? S equals 1 means we have a stock. That's on the I minus 1th day. But on ith day, we have s equals 0. That means on I minus 1th day, we hold a stock, but then we sold the stock on this guy, right? On ith day. That's why we have to add price here. So we have a plus here. And notice that we have a s equals 1 and s equals 0. So we are going from s of 1 comma 0. That's this guy. So we sold the stock. So that's what corresponds. So that's what this means. And we have to consider the case for s equals 1 for this guy. So that's what we have here. Very similar. So dp of I comma j comma 1. And we take the maximum of dp of I minus 1, j, and 1. Or dp of I minus 1 comma j minus 1 comma 0 minus price on ith day. Same thing. For the first guy, we didn't do anything. For the second guy, it means that we didn't have a stock on I minus 1th day, but we chose to buy. We chose to buy a stock. Therefore, we spend the price of ith day. So that's why you have this minus here. And we take the maximum. And that's what we do. And that's basically how we fill out our three-dimensional DP table. Now we have to consider our base case, initial condition here. In that case, it'll be this guy. Looks very complicated, but let's just for the moment, bear with me. So we have a dp of I dp of minus 1 comma j comma 0 equals dp of I comma 0 comma 0, and that's equal to, we set that equal to 0 for all I and j, meaning that like j, for any value of j, like j equals 1 to like 0k, something like that, it's all equal to 0. Set that to equal to 0, and I will explain what this means in just few minutes later. For the next case, we have dp of minus 1 comma j comma 1, and that's also equal to dp of I comma 0 comma 1, and we set that equal to negative infinity for all I and j in our natural number. So negative infinity means we come up with, we say that that's something that can never happen, right? Remember, dp is the maximum profit we can get. Let's see what that means. As I wrote here, negative infinity means that these states can never happen. To denote impossibility of our case, of our states, we just set that equal to negative infinity because we are taking the maximum here. It will work out. If we have, say, we have to find the minimum of something, then we can set that equal to positive infinity for impossible cases. But for now, we have to deal with maximum profit. So we set that equal to negative infinity. dp of negative 1 comma j comma 0, that's this guy, then that's equal to 0. Why is that? Well, on I equals negative 1, that's remember that our price, we have a 0 index, right? I minus 1 means like we haven't traded a stock yet, and so the profit is 0. Like this guy, dp of I minus 1, dp of minus 1 comma j comma 1. Now remember, I equals negative 1 means we haven't traded a stock, and then it is impossible to sell a stock. We have a 1 here. That means we sell a stock, right? But we have a I equals negative 1, and this is impossible to happen, right? So that's why we set that equal to negative infinity. Here we also have a dp of I comma 0 comma 0, and that's set to 0 for all I in natural number. And that's because why? Here we have 0, so no transaction is allowed. So if no transaction is allowed, that means you cannot buy and sell a stock. So the maximum profit is just 0, right? That makes sense. And here dp of I comma 0 comma 1 is equal to negative infinity for all I in natural number. So again, we are in a case where, we are in a situation where no transaction is allowed. It is impossible to sell a stock, right? So we have a negative infinity there. So that's the base case, our initial condition. And our code for all the 6 problems looks something like this. We initialize our dp variable, dp matrix. So dp matrix is initialized. And then we have a for loop here, 2 for loops. Since here for since we have 2 states for s, we don't actually have to run 3 for loops. But if we have, say, 10 states for some hypothetical problems, then yeah, we have to run 3 for loops. So in this case, we don't have to use third for loop, so that's good for us. Yeah, so for I is in range from 0, 1, 2 all the way to n minus 1. That's this part. For j from k, k minus 1, k minus 2 all the way to 1. All right, and then we have to check whether we are in a base case or not. So if I is equal to 0, then that means we are in a base case. So we run this guy, and then if we are not in a base case, then we run this guy. Well, they look the same, right? But then here, this one will greatly simplify these guys. So for instance, dp of this guy, what is this guy? Let me use different color. So what is this guy? So this one is what? I is any number. I can be any number. J, and so we have this. I'm sorry. I is -1, and j can be any number. So is this guy, right? So we have this is equal to 0, and dp of -1, comma j, comma 1, that is -infinity, right? So we have, so we use different colors. So that's this guy. So that would be -infinity plus some price of 0. So you take the maximum, and this one is 0, right? So this is 0. And for this guy, dp of -1, comma j, comma 1, what is this guy? That's -infinity, right? Because here, that means we sell a stock. But you cannot sell a stock on I equals -1. And then we have this guy. That one is 0, and we have a minus. So we have a 0 minus price of 0. So you take the maximum of these two, then we get negative price. So this one will be negative price of 0, something like that. And then this guy, you just run a typical DP matrix. We fill out the DP matrix, and we return this guy. Notice that we use 0, not 1. Why is that? Oh, that's because this is always bigger than this guy. 1 means what? So 1 means we have a stock, right? So if you look at here, say, so s equals 1 means we have a stock, right? And s equals 0 means we don't have a stock. So that means we sold a stock. When you sell a stock, you at least gain some, you get some profit. So that's why this guy is always bigger than this guy. Yeah, so I think that's it. That's for this problem, and let's actually work on the problem. Okay. All right. So this is my code for problem 188, and one thing that I want to mention is, remember, if you look at the constraint here, we have our length of price is from 0 to 1000. If you look at all other problems, the length of price is actually greater than 0. So it starts from 1. So that's one thing that you have to keep in mind. So that's why I added this, we check the case if we have a, empty array, then we return 0. So that's for this part. Here we initialize, our DP matrix. We have a, initial condition, base case. So what does this mean? This means we have a impossible case to happen. This guy is 0. That means we have no transaction allowed, and you cannot sell a stock, right? So this 1 means we are selling a stock. So that's why this is equal to -infinity for all I from 0 to n minus 1. And then here is just, our, two for loops that you just saw. This is our base case. And we have simplified this part, so that's it. And let's run this. So that's for problem 188, and let's look at the remaining 5 problems. They are very similar. So this is the second problem of our series, and here you can see that, well, first, one thing you have to notice is that, look at this one. So the length of price is always greater than 0. So that's something that you have to keep in mind for the previous problem. I think that was a little bit dumb, but it is what it is. For this problem, we have at most 2 transactions. That means our K will be 2. Yeah, here you can see instead of K, I think we have 2 here. And that's pretty much it for this problem. So let's run this. Okay, so well, this one works. So this my code works. Actually, for this problem, you don't have to run 2 for loops here. Why is that? Because just like here, we have 2 cases to consider, right? J is only what from 2 and 1, right? You can actually run a one for loop to solve this problem. I will leave that as an exercise for you guys. If you want to know, if you want to know the answer, just write a comment and I will help you out. Okay, I can give you a solution for that for this case where you have a just one for loop instead of 2 for loops here. But I really want you guys to try this on your own. And let's look at our third problem. Okay, so as you can see, this is my code on the right hand side. Here, what do you notice? The difference is that in this problem, K, that's the number of transactions, is there is no restriction on the number of transactions. So K in this case will be infinity. Well, infinity in quote because K cannot be infinity, right? Because K is actually at most equal to the length of price. That's what we have since, well, if K is like, let's say a quote positive infinity, then K minus 1, K minus 2, K minus 3, they are all the same. You don't have to write the for loop for that K part. So here we only have one for loop here for I in range of n, and then this is what we have. So let's run this. Okay, so that's for this problem, and let's look at our fourth problem. This is our fourth problem in our in this video. And if you look at this problem, what do you notice? Here K is what? Yeah, you can only have one transaction in this case. Let's run this. Let's run our code and see what we get. So yeah, so this is some comment I made for you guys, and okay, let's run this. Ooh, so you could modify this a little bit to speed it up. Just want to show that this code works. And let's look at our fifth problem. This is our fifth problem in our series. And the only difference for this problem compared to others is that we have a cooldown. So when you sell a stock, you cannot buy the stock on the next day. So that cooldown will affect only this guy. So instead of I minus 1 here, we have I minus 2. That's it. That's for that. And because of that, because we have I minus 2, we have to consider another base case here. So that's this guy, base case for this problem. This base case was the same for other problem. So this base case was identical for other problems. Because here when we are at say I equals 1, that means we have this guy will become dp of I minus 2, which is dp of negative 1, right? But dp of negative 1 comma something blah 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 doesn't exist in our dp table. So that's why that's why I have this guy in our else if statement. So anyway, let's run this. That's for this problem. And how many problems do we have left? Oh, right. So we have only one problem left. So let's look at our last problem and see and get over with this DP. Yay. So this is our last problem. Well, thank you so much for sticking with me, and let's just get to this problem. So here, I didn't simplify this, but you guys will know what this one should be and what this one should be, right? So this one should be just negative price I. So this one will be negative price I, and then this one will be 0. Anyway, so that's for this. And so for this problem we have a fee, and I actually didn't get this right because on my first try, because I thought the fee only applies when you are buying it. But so that's why initially I had this instead of this. But apparently you incur a fee when you are selling the stock. So anyway, I think in the interview setting, you can ask your interviewer to clarify like how the fee, when does fee occurs? Like, do you pay your fee when you're buying a stock, or do you pay a fee when you're selling a stock, right? Because I mean, if you buy option or call options, or that you buy you have a premium, right? And then you have a expense when you're buying a core option. So anyway, this kind of problem, you just ask your interviewer to see like where you pay your fee. Is it buying or selling, or is it both, right? So anyway, for this problem, that's the only difference. You have you incur a fee, and that's it. So let's see. Let's run this. And there you go. So that concludes for our video on this dynamic programming series. And yeah, for some reason, I don't know why, for that problem it had 0. So anyway, hope you guys learn something from this video. And like dynamic programming, a lot of these interview problems are short. Like if you look at, say, if you take dynamic programming class, like real dynamic programming class, is very complicated, and codes are like I think you write many lines of code for those classes. But for interview setting, like usually dynamic programming problems are very short. The only difficulty is that you really have to think carefully about how to define your DP. Once you do that, you have to find the recurrence relationship, and then base case typically is like the easiest among those three. But just be very careful how to set up your DP. And for the next video, for the next video on dynamic programming, I can do house robber. That also has 5-6 problems, god knows how many. I can work on that, or I can actually pull some dynamic programming problems from the textbook and see how it is different from our interview setting. Oh, and the reason why I put the picture of Jim Simons and Edward Thorpe on my thumbnail is that Jim Simons actually hired a lot of, say, NLP researchers from IBM lab in natural language processing. I mean, NLP class, you have something called HMM, hidden Markov model. And I don't know if you guys have taken those classes, or if you have seen that algorithm. Beneath that HMM is that it uses dynamic programming. So that's why I put those two people's portrait in my thumbnail. And yeah, anyway, that's for that. And so next video I can talk about house robber problems. Anyway, thank you so much, you guys, for sticking with me for this long video, and hope you guys learned something from this video. That's pretty much it, and I hope you guys have a great evening, and I'll see you next time. Bye bye.